So here's our second example that's going to talk about using a table to calculate the equilibrium constant, right? And remember, we're going to follow the exact same procedure that we just did. And if you want to give it a go, I think you should feel comfortable enough to let this, do this one on your own, and then play the video further to see if the answer is correct. Okay, I'm just going to give you one more hint over here. This is, my word, my apologies. This over here is in the aqueous. This is an aqueous solution. It's also an aqueous solution, right? This is also aqueous. And this over here is a pure liquid. Okay, so let's pause. Why don't you do it? Follow the steps, write out the equation, do the table, draw all your stars, use ratio and proportion, fill in everything, and then calculate the value of Kc. Okay. Okay, so I hope you've done that. So I'm going to go through it now with you over here. Remember, step one is to draw your lines under these arrows, right, so that you can, let's see as straight as we can get it over there. Okay, now for the purposes of this calculation, although the reaction is written out and you can calculate everything else for H2O, I'm just going to leave it out of my calculation. In fact, you can put it in. Let's just put it in, but then I'll leave out the column in terms of what I calculate over there. Okay, right. And then let's just put this thing over here, and let's just put one there below. Okay, and there's my table for now. What I want to do in the meantime is I want to add initial, and then reacted or produced, and then equilibrium, and then the equilibrium concentration, right? And that thing over there is equal to N over V. And here we're going to see an example where the V is a little bit different to the previous one. Okay, so let's just draw the lines across once again. And I'm setting up my table. Okay, and that's the final row over there. Now we're not yet done. Remember, I said you still need to draw stars, and the stars will remind us of ratio and proportion. And this example is quite easy because everything is balanced and they work in a ratio. The ratio over here is 1 is to 1 is to 1 is to 1. And the reason for that is that's 1, that's 1, that's 1, that's 1. And you can count everything to see if this thing is perfectly balanced, which it should be because esters will usually be. Okay? This is my reactant side, these are my product side. And this should be a reversible reaction. Okay. Okay. So let's read the question carefully. It says, at the beginning of the reaction, there are 0.5 moles of ethanoic acid and 0.5 moles of ethanol. So this is Cu, that's my ethanoic acid, and this is my ethanol because you see the OH molecule over there, or functional group, hydroxyl functional group. Okay, and on this side it gives me ethyl ethanoate plus water. Okay, now I'm going to leave out the entire column over here because I know that the equilibrium concentrations of a solid or pure liquid is just 1. So my answer over here is 1 either way. Okay, so I'm going to ignore this entire column. Remember, columns are vertical. And if we read the question carefully, it says the volume of the reaction container is 2 decimeters cubed. Okay. So let's see what that does. So let's fill in all the information given. The beginning of the reaction, there's 0.5 moles of ethanoic acid, so that's 0.5. Okay. And 0.5 moles of ethanol. Do they give us anything to say that there's any ethyl ethanoate in the reaction? No. So we assume that there's none of that, and obviously there's none of that as well. Okay. I think let us just work out this one here anyway. That's going to be 0. Okay. Because seeing that I have the column there. But remember, because this is liquids, let's just write in the final answer there. That's going to be 1. Irrespective of what the calculation reveals, just because it's a liquid and it's not considered for this purposes. Okay. Right, now it says at equilibrium, so we're done with that. and we're done with that. That's already in our table. That's already in our table now. At equilibrium, 0.3 moles of ethanoic acid was left unreacted. So this is the ethanoic acid, CH3COOH, and equilibrium, I'm only left with 0.3 of it. Equilibrium, there's still 0.3 left. Now you ask yourself, Imaad, or whoever you are, 0.5 became 0.3. Did I minus or did I add? I minus, right? And now everything, if I have a minus on this side of the sign, everything on that side of the sign must have minuses, and everything on the other side of the sign must have pluses. Okay, that's examining the change. Now we get to the real crux of the work. 0.5 minus what gives me 0.3? The answer is 0.2. Now because of the stars, I need to fill in this entire row in terms of the ratio and proportion that I see present over here. Okay, so that's 0.2, and that's 1:1:1:1, so all of this must be 0.2. Right, because it's 1:1:1:1. They must just be identical. 1 cup of flour, 1 egg gives me 1 cake and 1 drink, or whatever you want to call it. Okay, and so this also has to technically be 0.2, and the rest is just simple algebra. 0.5 minus 0.2 is 0.3. 0.0 plus 0.2 gives me 0.2, and 0 plus 0.2 is also going to give me 0.2. Okay, we're going to ignore this one over here because that was a liquid. The others we're going to calculate properly. We're going to say 0.3 divided by 2. So we say 0.3 divided by the volume, and the volume over here is 2. That must give me a value of 0.15. Same thing over here, 0.3 divided by 2 has to give me 0.15. And this thing over here is going to give me 0.2 divided by 2, and that must give me 0.1. Okay, so these three values are the values you're going to use in your Kc formula. You can leave out the pure liquid or the solid in this case. So let's write it down on this side. Kc is equal to the concentration of ethyl ethanoate, CH3, COOCH, okay, that's a long one, COOCH2, CH3, right, raised to the power of 1, divided by the following, which has to be CH3, COOH, Cu, raised to the power of 1, because it's all 1:1:1:1. And you see I've left out the H2O because it's just got a value of 1. Okay, in this case over here, and I think for the sake of the formula you can write it in. Okay, this one over here has CH3, CH2OH. Okay, and now let's substitute the actual values we found. Remember, this one here you can leave it out because it has a value of 1, but just to show you where the 1's coming from because of it being a pure liquid, it's not considered really for this calculation, but we'll write it in just so that you can see what it is. This one's going to be 0.1 because that's taken from here. Then the reactants we have 0.15, sorry, multiplied by 0.15. Okay, and let's see what that gives us. 0.1, you can do this on your calculator, divided by 0.15, multiplied by 0.15. It's going to give me 4,44. And once again, the Kc value has got no units needed for Kc because they're all